Well, welcome to the second keynote within the Design 2020 conference. I'm John Clarkson. I'm a professor of engineering design at the University of Cambridge and a part of the program committee for the conference. Well, welcome to the second keynote. And it's a huge delight for me to invite Zehavit Reisin, who is Vice President and Head of Materials Business within Stratasys. And she heads up the Europe, Middle East and Africa, Asia, Pacific and Japan unit since 2018. And prior to that, she was head of the Rapid Prototyping Business Unit between 2016 and 2018. She brings over 25 years of project and business management expertise in the printing industry, having worked with Scitex, Creo and Kodak in the past. And she holds an MA and a BA in physics from the Tel Aviv University and is a graduate of the Senior Business Management course at the Recanati Graduate School for Business at the same university. So, Zehavit, over to you to give your presentation. Thank you.
Thank you very much. And it's my great pleasure and honor to attend this session today. The topic would be what's new with materials. And as discussed before, we would like to show how through materials and innovation, we can reach new levels of design, whether it has to do with engineering applications or pure industrial design applications. So let us look at the role of 3D printing materials. And actually, it's how well the materials meet three applications. I'm trying to simplify things for us. The first application would be prototyping, which is kind of divided into concept. This is the stage at which you would like to have quick and dirty work, I would say. Draft would be a nice word in this case. Low-cost iterations will be the name of the game. Quality, which is good enough, will be acceptable, and accordingly, the requirements from the material. But when it comes to design or engineering, and again, we are discussing the prototyping stage, the materials should meet dimensional stability requirements, which imply high deflection temperature, which imply strengths and impact, and additional properties. But prototyping to be the stage at which we mimic and simulate the end-use part require from materials, mainly at this stage, the necessary dimensional stability and some functional performance. Another application is tooling. This is where we discuss jigs and fixtures that could be at the manufacturing hall or even molding. Here, obviously, the materials will need to acquire more properties. This is where the materials should not just be with dimensional stability, but with some thermal coefficient of, with some specific thermal coefficient, with ability to withstand rigorous materials that are being jetted into mold, for example, and other properties. Chemical resistance will not harm as well. And the last one, the last and most attractive application is the manufacturing. And this is not about simulating end-use parts or being close in functional performance. This is about the end-use parts. And here the materials should be exactly with the performance of the end-use parts. So this is how we categorize our materials. And in our company at Stratasys, we focus for the last 30 years on two technologies, two different ones. One, which is younger, this is the polyjet technology, which was born in Israel. And it's all about photopolymers, acrylic-based photopolymers that are being jetted, model material and support, very thin layers, can be 14 micron layers, being added one on top of the other, and being cured instantly with UV. You can see here that I highlight precision to be the main characteristic here. At the same time, we have FDM, the thermoplastics materials technology, fusion deposition modeling, which is using extrusion of filaments that are basically thermoplastics, real thermoplastics from ABS all the way to ULTEM. And with both technologies, which are both additive, we reach precision on one hand, performance on the other hand. These are the core competencies of each technology. And when we translate that into the type of parts that can be produced, we can see that PolyJet is really about aesthetics, visual. It's about colors, look and feel, rubber, simulating polypropylene, smooth surfaces, transparency, where the other side of the house is FDM performance, which is all about durable ABS, nylon 12 carbon fiber, ULTEM family for high heat resistance and amazing impact, and UV resistant ASA materials. So if we want to remember it very easily, PolyJet, it's about precision and beauty, I would say. So we can remember visual aesthetics. And FDM is really about functional and performance. And the reason those technologies were developed and acquired by us is because customers need that. Customer needs complementary offering that will take them throughout the entire life cycle of a prototype all the way to the end use part. A quick look at this chart shows us exactly the difference between acrylic-based photopolymers with PolyJet technology and thermoplastics materials on FDM. The y-axis is the heat deflection temperature resistance. The x-axis is the impact in joule per meter. It's easy to see that the lower quadrant of the chart is all PolyJet materials, and they have particular impact and HDT, which can be surrounded with 100 degrees for HDT and 100 joule per meters in terms of impact. But when it comes to functional and end-use parts, FDM technology can help us. And you can see right here at the top of the chart, very high temperature materials, or alternatively, very high impact materials that belongs to FDM. So as I said at the beginning, beauty and precision with the PolyJet, fine details, and functional and performance with the FDM. So let me take you through a quick tour, which is our journey with PolyJet technology, firstly towards the perfect prototype. So it all started in Israel in 2000, and we started with single material jetting, just one material being jetted, and of course support material in order to help hinges and where gravitation will just make the part not durable. So Quadra and Eden were all single material technology, and that's all we could print. It was 2007 that I stood in Euromold stage and announced something revolutionary. We can now jet two materials simultaneously using Connex platform. So what's that all about, this ability to jet two materials? I'll take a minute to explain that, because that will be the baseline of everything you will see today when it comes to design realism by Stratasys. So we are able to generate digital materials. The first material could be rigid or flexible. A second one that is jetted simultaneously could be as well rigid or flexible. The outcome would be a composite material, which is digital material, digital in the sense that in the machine, all I have is one cartridge, which is rigid, and one cartridge, which is flexible. And the digital material is composed on the fly, on the voxel level, and create a completely different set of mechanical and thermal properties, in fact, creates a new material. This was the basis of multi-material technology by Stratasys and the ability to generate digital materials. In 2007, there were only 21 combinations, and you can see that it was about rigid and rubber prototypes. Same color, a little bit of grays, some shades of gray and white. That's all we could do. But then it was 2011 that we say, hey, why don't we take this technology of digital materials, not just to rigid and rubber? Let's take, for example, high temperature material and compose it with high toughness material. And this is exactly how we arrived to our digital ABS that you can see the mold in the picture, because that's what brought to, again, a material that is composed on the fly with ABS-like properties. We didn't say that this is enough for us and continued into a platform that is able to jet simultaneously 3 modeling material, not just 2, but 3. What can one do with 3 materials? Well, that was the start of color realism. The ability to do basic color. This is not about accurate color. This is about cyan, magenta, yellow. That's it. This is 3 materials. But also we could take the digital ABS and rubber and create functional models such as overmolding or different shore values. All that happened back in 2013. We continued in 2016, this time jetting 7 different materials. It was 6 modeling materials and 1 support to enable full color for the first time. Later on, 2019, introducing J8 series with 7 modeling material, and recently took all this beauty of full color into the office environment with our J55. I'd like to really describe this revolution of full color with multi-material technology through our customer, Ryan Berger. He's a senior industrial designer at Priority Designs in the USA. He's showing this part and he says, this is a product we developed for a client. It has certain combined brand elements, graphics, colors, textures, all layered under clear material. This job traditionally is a multi-week process with a lot of manual complexity, man hours, and cost. And to me, he said, lots of errors. And indeed, this brings us to the designer pains today. The designer would like to be able to communicate in confidence the intent. You can see here that this is a massage gun, and the customer, this is our designer, had to use previously rendering illustrations or single material 3D prints to convey the message and to pray and hope that the decision maker really got his idea, because if the decision maker will see the full design at the very end, that will be after 9 months, it will be too late in the process and the cost of error will be unacceptable. But what if the same Ryan Berger could show this out of the printer and eliminate any communication issues because it's straightforward what the final part will look like? This is a major pain today, to be able and create the final part realism model at the same time you do the concept and get the feedback from your superior to continue into the final production series. And not to mention intellectual property. When you have it all in-house, intellectual property is the very important and significant thing for you to keep in-house. So what if basically a designer could do concepts and then detailed design, and then to choose color, material, and finish, as it is called in the professional language, CMF, and get high fidelity model right off the printer. So it's not about just rendering illustrations. It's about a tangible prototype, which reduces modeling time and cut modeling costs. It's about keeping everything in-house. And in the case of the latest machine we launched in April, J55, it's really about compact, quiet, non-toxic, and fit to a room machine. Coming back to Ryan Berger, that's what he said. That, meaning this product, can be done overnight on the J55. Off the printer, that's what you see. So this is exactly the revolution I'm talking about, and I'd like to detail a little bit some design realism capabilities that can be translated into daily applications. So we decided to bring the best red in 3D printing. No more pink or slightly red, but exact best red. And you can see in the picture that the PolyJet prototype and the original are very difficult to differentiate between. And this was with a new set of resins which were actually translucent and enabled us a wider gamut than before and great red that took us into the industry of lighting. We took this further with cyan, magenta, yellow, vivid resins and got into industries as packaging, consumer goods, and more. We also worked on color, starting to work on color back then very seriously, understanding that in order to translate the designer intent into the printer, into the way the printed part will look like, we must adjust color profiles so they are smooth and easy to understand and easy to follow as far as designer intent is concerned. So a lot of effort around our GrabCAD software. And we didn't say that's all we need to do around rigid material, which I talked about so far. We said, let's move into rubber as well, introducing Agilus 30, a rubber-like material at Show 30. And then we were able to use Agilus digital material with color to create color in rubber. And the fact that rubber and color were composed together was not just for achieving color in rubber. It was for achieving textures. And we can see here beautiful textures that are mimicking jeans, marble, wood, all out of the printer. This was the first time that something like that was seen in the industry. And here comes a typical communication issue. I need this part to be blue as the ocean, but actually my designer meant blue like his eyes. Why don't we use a standard to define exactly which blue we need? And this is where I personally signed this agreement with Pantone, which validated colors on our J series. So when you select the color, you can actually select Pantone color, and that will be completely expressed as it was validated by Pantone with the colors, which are digital materials on our machine. Here is an example of Audi A3 taillight. It's not the final product. We are still in prototyping. But look how this prototype, which is aimed to mimic, remember the objective, to mimic completely the end-use part, look, feel, and function. We can see here a taillight at the exact color after printing and polishing. And the cost saving here and the time saving here was quite enormous versus traditional processes which involve molding and CNC and others. Another example which I really like is this one for the armrest. This armrest came like that out of the printer, just like that, with the stitches, with the leather, all of that came just like that. To remind us all, traditionally, this process is an 8-step CNC, handcrafting the base, preparing and applying leather. Many, many steps. With our solution on Stratasys, with the acrylic-based resins, we are able to reduce the cost in 85% and make it 4.5 times faster. And to be honest, beyond those numbers, it's really about the communication. How a designer can communicate it all in an accurate way, so the stitches will look like that, so the base will look like that, so the buttons will serve the functionality they need. This is the main challenge, and this has been solved with 3D printing. In this example of Aeroflex, this is about consumer packaging, and here we can see usage of Pantone. Again, the idea was to get the exact red or the exact blue that this packaging required. So no need to guess or do iteration. It just spot on with this color. Academic research which loves multi-material because of the digital combinations, because of the ability really to get to the voxel level, this three-dimensional pixel, if you wish, and control it. Be able to control the voxel level with properties, with appearance from opacity to translucity, and all those projects are highly adopted by top academic research institutes all over the world. This was all enabled with our J series, and sorry, something. Oops. Yeah. So a minute before we get into more innovation, up until now, all this design realism that I talked about worked with PolyJet technology, which is based, as I said, on acrylic-based resins, but it's really about printing block that moves along the X and Y axis, build platform that moves in the Z direction layer by layer, drops of photopolymer that are deposited on the building tray, and then exposure to UV light to complete polymerization. It was all about Cartesian systems. It was only now that we introduced the J55 technology, which is using a rotational tray. And what happens here is that the print head does not move. The print head is static, taking motion out of the print head, and that allows for consistent material jetting. Hence, the print quality is amazing. And of course, 5 modeling materials are jetted here simultaneously for full color models in hand and fast. So from Cartesian to rotational tray, specifically for the office environment, this was our latest and greatest innovation. So far for prototyping using PolyJet technology, and here comes the FDM world, the fusion deposition modeling using true thermoplastics. And I'd like to draw your attention to an interesting material that we launched 2 years ago. It was nylon 12 carbon fiber. And with nylon 12 carbon fiber, we are able to replace metal parts. Basically, we implemented 35% chopped carbon fiber by weight. You can see it here under the electrical microscope. And that provided the following properties. For the first time, we got tensile strengths. That is the top one that we have among Stratasys FDM materials. The same for the specific stiffness and, of course, the modulus. This enables everyone to understand that this is the strongest material that we have. It is indeed with carbon fiber field, chopped carbon fiber, and it allows us to replace metal parts. In this example, we can see very easily that everything for the bike industry, if it's brake levers, chain guards, foot pegs, all these which are made of metal for the prototyping stage can now be produced with nylon 12 carbon fiber. And of course, this is about lightweight, reduced part cost, and increasing performance. I'd like to share a quick movie from Utah Trikes that shows how nylon 12 carbon fiber is being used.
My name is Ashley Guy, and I'm the president and founder of Utah Trikes. We have built our business on customization, and 3D printing has led us to the next level. So Nylon 12 CF has made 3D printing a production reality. We can make parts faster. We can go to prototype within just a couple weeks. Not even just prototypes, but we can actually design a part that we know will work from experience, print it out, and a couple hours later, we now have a viable part. Parts that would flex with nylon 12 were as stiff as we needed them to be now with the nylon 12 CF, and parts that would potentially break with the Ultim 1010 were now as strong as we needed them to be. Nylon 12 CF material has really reached into almost all aspects of our production at this point. We're using it for jigs and fixtures, drill guides, machine tools. The increased efficiency that this material and process has given us allows us to spend more time with our customers, more time growing our business and becoming more productive than ever. This has made our customers happier, it's made our employees happier, and it's made our accountant happier.
So far for prototyping with nylon 12 carbon fiber using FDM technology. When we get to the tooling world, we can use both FDM and PolyJet technology. We can leverage 3D printing for manufacturing tooling that otherwise would cost a lot, much more than 3D printed parts, and would take so many more months. This is the scale I'm talking here, months than the days it can enable printing of these parts. So we have jigs and fixtures, we have injection molds that can be also with PolyJet technology, and we have robotic tools that can be done using 3D printing. In the picture here, we can see nylon 12 improved tooling with 3D printed parts. We can see how rocker molding and spoilers are being attached. We can see how assembly of the to the glass roof is being done with that, positioning of the nameplate, and it's all done with by Opel. That really was evident to lighter, stronger tools that enable very fast and cheap production line. On the injection molding front, we have our PolyJet digital ABS that can be used to print the mold, and then we could potentially jet low quantities for very advanced materials, but between 50 to 100 parts when it comes to ABS, ASA, etc. Manufacturing, as I said at the beginning, this is the sexiest part probably, where everyone would like to be there and use parts out of the printer. FDM technology would be here the major one, but I'll leave some surprise for the end that has to do with manufacturing from different way. So Airbus is the famous story at which we have now more than 1,000 flying parts 3D printed on our Fortus 900. Airbus commercial airliner is using it, and that actually increased dramatically the supply chain flexibility and enabled those parts because of the fact that the material has all the regulative approvals, FAA, it's a certified material. We worked a lot on getting all those approvals. The process was approved as well as the material components themselves. This is happening today, and the major material playing here is Ultem 9085. Another material that is taken mainly into the aerospace industry is Antero. This is PEC-based material, polyether ketone, that enables extremely good chemical resistance, which is needed when the part comes in contact with oil, with solvents, and does not deteriorate in performance due to this contact. While Ultem is called the king of the cabin, the Antero is our king or queen, if you wish, of outside the cabin parts. And it's really about temperature resistance, strong, and also ultra low outgazing, which is another measure for aerospace parts. And we took it even one further step and made the Antero ESD safe. So it has, on top of all the properties that I mentioned before, ESD performance. And here is the Orion spacecraft where the docking hatch was 3D printed with the Antero ESD. The end customer was extremely happy with the performance, and they are continuing to identify new applications. So that was about manufacturing, real end-use parts that serves aerospace sector, but also some in automotive or rail industry. So what about PolyJet? Is it really just about appearance and fine details and visual and precision? I would challenge that. And it's not just myself. It was Mini Cooper that decided to come up with end-use part made of PolyJet technology. This is actually a site in China of Mini Cooper, a website at which you could choose and customize parts that are full of textures and colors as only PolyJet technology can manufacture. And you apply for the exact custom part that you need with your name or any other thing, and this is the result. Next thing would be the front ones that will be also made this way. This is manufacturing. This is not a prototype. This is end-use parts. The key thing here is, because I like to be direct here, this is still the same acrylic-based photopolymers, which I showed you at the chart at the beginning, that cannot exceed very high heat deflection temperature or cannot be with extreme dimensional stability. There was a coating used here that made it so durable. And again, all the color and texture capabilities that came from the multi-material technology of PolyJet, that's what enabled this application. And another one that is coming up, and this is in technology feasibility, PolyJet end-use parts in fashion. We are discussing these days, and this is happening on the same J series platform, printing fashion, printing accessories with several fabrics. And this is happening as we speak with specific partners, customers that are partnering with us. And in 2021, this will become commercially available. So just to summarize, we went through the materials journey, and through that we understood the major applications of 3D printing: prototyping for engineering and design, tooling, and then the end-use parts. Both technologies presented can be used for each of the applications. However, each of them has its core competency and areas it will shine more than the other. So I'd like to thank you very much for your attention. And yeah, let's open the Q&A now. Thank you very much.
We don't hear the usual applause at this point, but I'm sure it's going on in rooms all around the world. So thank you very, very much for an extraordinary presentation. And I've certainly learned an enormous amount from the things you've shown me. It's just opened all sorts of ideas and opportunities. We've had some good questions come through while you've been speaking, so I'll pick them out one at a time from the list. So the first came in from David Jones, and thanking you for the presentation, and then asking the question, is the ability to recycle or dispose of environmentally friendly involved in the development of these new materials methods? So you're talking about recyclability when you're starting to mix the materials together.
Right. So recycling at the moment is more on the FDM side of the house than the PolyJet. So not the multi-material technology we discussed before. On the FDM side, we actually recycle the canisters. The canisters can be recycled, and we are using them in order to populate new thermoplastic filament. We fix them, make them nice, and reuse them. On the PolyJet side, not yet, but there are quite thoughts into the roadmap of the company to have a recyclable material, to be more green and friendly to the environment. You need to understand that a company as Stratasys always go hand in hand with regulation and comply with all the safety and needed regulations. So it's really a tough journey, but it's already in our roadmap. So FDM already happening, PolyJet hopefully in the future.
That's very helpful. And the next question from George picks up on something we talked about before we went on air, which was, where does this fit within the design process and who's it for? And his question is, there's an obvious link to the industrial designer, but maybe what would the link be for the mechanical designer? I think it links to the next question from Nicolo as to, at what point in the design process, and maybe for whom, are you targeting the use of this technology?
Okay, so when it comes to PolyJet technology, obviously in the last years, the focus is on the industrial design. But our comfort zone, okay, and install base of thousands of machines is the engineering design. And this is where we allow concepts with a low-cost material. It's called draft gray, for example, and then more engineering applications with polypropylene simulation, with rubber-like material, with digital ABS, with overmolding capabilities. The fact that we are able to jet simultaneously 2, 3, and recently 7 modeling materials enable different properties on the same part, different coatings, different thin walls performance. So it's all there, but the fact that we are using acrylic-based photopolymers a bit limit us. It limits us in how we can reach higher heat deflection temperature, higher impact, etc. But within the properties that can be achieved, we have all the playground that meet engineering needs. And the real thing is that this is happening as we speak with thousands of customers. So engineering is happening today and can grow further with new materials we are working on as far as functional performance with PolyJet. Industrial design, obviously with all the color and texture. And with the FDM technology, this is really all about engineering. There's the accuracy that is needed. There's the functional materials, as I said, from ABS, nylon 12 carbon fiber, Ultem family. All that is not just possible, but all about engineering applications.
That's again very helpful. So I'm going to skip the next question from George for the moment because he's got 3 questions up there. And we'll come back to that at the end. The next one's by Jeremy. Again, thanking you for the presentation, talking about looking at earlier generation models that generated quite a lot of resin waste. And the question is, has that been changed or is it different with the current technologies?
Yes, so in fact, we worked a lot about reducing waste. Waste is part of, or certain waste is part of the technology, and this is the reason, not the waste itself, but the fact that we are ironing, I would say, the layers gives us such great quality and fine details. However, we reduced the amount of waste in the recent J8 series. There's also no need to replace resin, which costs for itself waste, because you can work with a preset configuration of 7 modeling materials, whether these are color modeling materials or functional one like ABS or rubber or clear material. So no need to replace the resin, which was #1 reason for waste. You just keep working with the same configuration. And the overall waste was, of course, down to a more reasonable level.
That's great, thank you. And I think the next question by Daniela again is talking about recycling. A slightly different question here, and wondering about the ability to use recycled plastics with the technology, in particular, what influence do carbon reinforced polymers have in the performance of the recycling process?
Yeah, so as I said, our steps into recycling are mainly on the FDM material, and the recycling is more like reusage, okay? Reusage of canisters, empty canisters that are brought back to our production line and are being reused. So it's not proper recycling as someone would think. It's more of reusage. Also environmentally friendly, but not exactly. We still have a journey here. As I said, this is on our roadmap. It's quite tricky when it comes to thermoplastics, and on the other side, as I said, acrylic-based photopolymers, but we'll get there. It's a very strategic point in our vision into the future.
So we're back to George again, and a very interesting question about how stable are the materials over time?
Mm-hmm. So we need to talk about 2 different stages. The stage at which the material is liquid, in the case of PolyJet, and this is the resin status. It's liquid until it gets into the machine and being polymerized. So in this sense, the shelf life of our materials is so that most of them have 24 months from production. Obviously, on the way, there is the warehouse and the reseller and the end user. But I can say that there is no way that a customer will receive material with less than 6 months. Okay, after all this cycle that we talked about. So this is about what this liquid is all about. But when we talk about the part itself, I created a part out of the material. How durable is the part? So when we discuss PolyJet, the parts are mainly used for prototypes. So obviously people will use it for a couple of months and then will redo it, will reiterate. So by nature, it's not meant to be very durable. When it comes to FDM technology, where we really touch, as I showed in the aerospace flying parts and so on, these parts are very durable. Also, the thermoplastic itself, the filament, has shelf life. It doesn't have a shelf life, actually. Infinite shelf life. Of course, as long as kept properly under the correct humidity and storage instructions. So the thermoplastic filament, forever. The parts are very durable as they are made of thermoplastics, and the properties are superior to what we have in PolyJet technology. I hope I answered.
That's good, thank you. And the next question again is more about recycling, but could we use carbon fiber with recycled plastic to reduce and reuse the plastic?
We have not tried it yet. I do not have the answer, and as I said, we do not really use that for recycling. People are able, this is important to remember, polymerized part on the PolyJet we are able to throw them to regular trash if you wish, because there's no issue with that. It's not toxic, the polymerized part. Okay. On the FDM side, those that are made just of standard plastics, again, no problem to recycle them. With carbon fiber, we have not tried it enough, so I cannot guarantee that.
So the next question from Christina Shea, I think, picks up on some of the earlier questions. Are there any plans to improve the engineering functionality of the PolyJet materials to print end-use parts that are more functional than the example shown?
Yes, so this was quite a debate in the company, because we saw that the multi-material technology really gets us to be unique into a blue ocean for the industrial design world and replace traditional methods. So business-wise, we saw the potential there and less on the functional one, which we had a red ocean, as we say these days. However, it's still many customers of us that are looking for the fine details and the quality of PolyJet technology along with functional performance. So this is back on the table. And we are discussing exactly what will make a faster journey here, because usually developing materials for PolyJet technology is not a fast track experience. And we are discussing again how we can increase and make more functional materials for a wider range of applications. So yes, this is on the table.
So I wanted to come back maybe for the last question to something we talked about again before we came on air. And a lot of what you've presented and the questions allude to the fact that we have to begin to think differently as engineers and designers in designing things, because they can be made differently. And what is the aspiration that you or Stratasys have in terms of helping the next generation of engineers to think differently?
So firstly, I'm very happy that this message of think differently was well conveyed. This is exactly what we talk about, design for AM. It all starts with the design stage that is tailored for the additive manufacturing or printing technology. We are strongly in education institutes. It starts from colleges and even high schools, in some cases earlier than that. But if we speak about PolyJet technology, it's more about colleges and universities and research institutes and excellence centers that are established these days in universities. And we have special programs to make our technology more accessible. If it has to do with commercial terms, the material pricing, the hardware pricing, the whole program. And we come also with curriculum of what can be done in terms of workflow, materials, and applications. This is our investment in the next engineers generation, if you wish. So when they get to the next, the first job they have, they can say, I would like to implement additive manufacturing. I would like to implement 3D printing because I learned that it cuts costs, and I learned that it saves time, and I learned, most important, that it can unleash my creativity. So it's all about education focus, which we have today, and education programs unique to education institutes that we roll to the field.
That seems a great place to stop. And thank you so much. It's been a real privilege to listen to you and be inspired by what you've shown us today. And thank you for coming to our conference. We really appreciate that. And again, a virtual round of applause from everybody, I'm sure, in the room.
Thank you very much. Thanks a lot for everyone. Hope to see you all soon face to face.